Eccoci. Oh, good afternoon. It's our pleasure to welcome Dario Trevisan. Look how he's apparently so young, and if you look at his webpage, you see that he is as much as strong. So it's really a pleasure to have him here. He's how can I say, a global mathematician, because yes, of course, because his interest spans across mathematics, from probability till maybe computer science, theoretical computer science. So we are in good hand. And today, I guess he speaks about his very recent his very recent interest in the mathematics of neural network, random neural network. And so thank you, Dario. You had a lot of introducers today because so important speakers deserve so many introducers. And so the floor is yours. Thank you again.
Oh, thank you. Thanks for the kind introduction. I'm very honored to give a seminar. Unfortunately, I'm not there with you, but I try to stick to the plan. So you can all see the slides as I see. So you see the title is, as already mentioned, is about deep neural networks which converge to Gaussian processes, and I'll try to explain the link and my recent works, joint works with my collaborators, in particular concerning the quantitative convergence. Okay, so. What about the plan? The plan will try to introduce briefly the overall theme, which is not something I initiated. There's already some literature in the site, but we'll try to focus then to our specific approach, which is about collecting and quantify in terms of mathematical inequalities, so bounds that we call a priori and posterior bounds, but also more recent developments in the so-called training regime, so in the so-called neural tangent kernel approximation. And then I'll tell you a bit more about conclusion and possible future perspectives on this kind of research line. So, first of all, just as a general introduction and motivation, perhaps you don't need it, but you know it's everywhere. So deep neural networks more or less are becoming a synonym of machine learning and of artificial intelligence. I mean, in common language, they become more or less the same. Perhaps people use AI as a general term, but deep neural networks are really what, I mean, are the driving the driving force underneath artificial intelligence applications. Nowadays, most of them, in particular in the recognition and generation of speech and visual samples, but also feature extractions and, of course, classification, but also, as I told you, generation of new data. So, and of course, mathematicians are faced with the problem of understanding and possibly drive, or at least give some directions about why some deep learning methods, so applications of deep neural networks, and of course all the numerical optimization which is underneath work. And of course, there are many interesting approaches. And okay, I have many interests, but probability is essentially my background. So we'll try to analyze in terms of probability and statistics, possibly also statistical physics give a lot of interesting interpretations of why deep learning works. But also there are other areas which are interested as well in the deep learning, also functional analysis, geometry, optimal control, and so on. So there's a huge motivated interest in this kind of questions, and let me move essentially to the basic structure and just to fix some notation on what we're going to understand and to analyze in this talk. Okay, so neural networks, if you don't know it already, are somehow biologically inspired ways to parameterize the functions, and these functions, say, takes as input vectors in R and 0, so n0 components, and as output, for example, they may be also one-dimensional, but more generally NL dimensional vectors. And the important part is usually these networks are built as compositions, stacked compositions of very simple pieces. Essentially, they use a linear or affine map and then some nonlinearities. Of course, the way you compose these things may be relevant, so not all the ways are interesting. And more or less, some architectures, so some ways to compose these functions are more effective than others. Also, this is an interesting question: why some neural networks perform better than others in the task we want to perform. Anyway, still keeping the exposition general, a lot of terminology already. Neural networks is something which somehow is borrowed from biology. So we would like to mimic somehow the architecture of our brain or of animals' brains, but also other terms like neurons, activation functions, connections, training are mostly borrowed from biology or neuroscience. But also some fundamental structures like the convolutional architectures are also taken more or less not really straightforwardly from biology, but somehow inspired by biology. So we have all this theory, which fundamentally is about parametrizing in a clever way functions that may be nonlinear, but in a way that we want to perform well for some tasks. So typically, graphically, if you want to just to stick with the simplest architecture, these are represented like this. So you have an input layer, which represents here a vector in R3. So we just draw with balls, with vertices, if you want, in a graph with nodes, the components, and then we have the linear function. In this case, we just take an affine function from R3 to R4, and we enter the first hidden layer. Once you are in the first so-called hidden layer, you are still not having something nonlinear because you just acted with a linear function. But that inside this blue nodes, if you want, you act component-wise with some nonlinearity, and then you have constructed something which is nonlinear, but that's not enough for you. For example, you may want to compose with another linear function and a map from R4 to R3, so you end up into the second hidden layer, and then maybe you again act with some nonlinearity, so-called activation function, and then finally another linear function, you end up in the so-called output layer. So if you want, this is a toy version of what is a general so-called also fully connected feed-forward neural network, which takes as input a vector in R3 and output a vector in R2. But of course, inside you have a lot of flexibility because you can choose the linear maps. And typically what you want to do is to find a right choice of the intermediate linear maps. Usually the nonlinearities are fixed, and you want just to find a way to choose the correct weights, so-called weights, which are just the coefficients in these linear maps, to find a good function that performs well for your task. Your task might be, for example, you have a position in R3 and you want to evaluate some function of the position. Okay. Now, of course, this is just one way to parameterize functions. We know of other ways like polynomials and stuff. So why neural networks are interesting? Well, neural networks become interesting because somehow the architecture is related to the task you want to study. And this approach, so to link the architecture to somehow the task you want to study, can be understood. I mean, at least this is not only my point, but also a general point in the literature. This can be also understood by taking a suitable limit. So essentially, to understand how these functions are built, we just look at a limit. Which limit? Well, you can take many limits in this case. For example, you can take a limit where the input becomes infinite or infinite dimensional, or also the output changes. Or if you want, this is the limit you are going to study, we study the limit of this so-called infinite width. So we take these intermediate layers that are hidden, so you don't see it from the input and output, and we let them grow. Okay, so we study the so-called scaling limit of large neural networks, not the deep limit. So we take the number of hidden layers fixed, typically. You can also let that number to infinity, but we fix that depth, and we take the large limit. And also, we don't want to study a specific network. We want somehow say something about a generic neural network in this limit. So what we do, we take random coefficients. So we take these random, these linear maps to be random matrices, if you want, random coefficients. Okay, now I'll tell you a bit more in which sense these are random and why some regimes are interested and some other are not. Anyway, you may say, okay, this is just an idea, an intuition, why this is interesting. Well, there are other reasons, maybe more motivated, more grounded in the theory. For example, you may think of this, since you want to learn to estimate a good function from a set of all the possible functions of all the neural networks, you may think of taking random functions as a way, from a Bayesian point of view, to put a prior distribution over your set of functions. These prior distributions over the functions is actually encoded in the prior distributions over the parameters, the weights, and also the so-called biases. But you can think of weights as a general term for parameters. Okay, biases are just the additive constants you add in the affine maps. Okay. Anyway, so you can think in Bayesian terms, if you like, Bayes' theorem and the Bayesian statistics. But more practically, you may also think that what happens in practice, and this is usually done and performed, is to find the correct function. You use some training algorithms. You take, for example, a cost function you try to minimize using gradient descent or stochastic gradient descent. And for these algorithms, you need a good initialization. And typically, this initialization, to be good, must be not too special. So you take what is called a random initialization. You take a random sample of your weights and biases, and you just start from that random function, and then you try to optimize. There's also a third point of view, if you want to motivate this kind of analysis, is that typically people realize that you don't even need to train all the parameters. Sometimes just picking a large enough random neural network may be already a good starting point, and maybe you just train a fraction of the parameters, like the last layer. So in this picture here, you may be okay, for example, by picking this random, the first and second layer random, and just the third layer, you just look at if you want a linear regression problem, if you take a squared loss. Okay, so essentially, there are many ways to motivate this, and so we are not the first one trying to understand analytically what's happening. And of course, if you want to really to go back to the beginnings, well, already Rosenblatt in his first work, where he actually introduced the concept of perceptron, so what we in modern terms call the neural network, but also more from a mathematical and statistical point of view. There are these works by Neal in the 90s, where he studied the single hidden layer limit. And recently, since neural networks in the so-called deep architecture, so where you stack more and more of these layers, have found more applications, and apparently they perform much better for certain tasks. There are some works by Matthews and Lee I want to cite, but also there are more recent developments of this. Well, now let me give you, I hope I motivated enough, just a brief sketch of our result. Essentially, what are we able to prove? So we are able to provide what I know for the first time, or at least say for a reasonable, with a reasonable rate, we are going to provide explicit quantitative bounds for an approximation of this deep neural network with random parameters and the so-called Gaussian approximation. So the interesting thing is that we can always, if you want, approximate a neural network if it is sufficiently wide, and if the parameters are sufficiently random, in the sense that these are independent and they have they don't have too much correlation. Okay, why this is the case? Well, this is an idea that goes back to Neal. Essentially, if you are in a good central limit theorem regime, whatever you do, even if it is not linear, at some point some sort of averaging out will appear, so you will have a central limit theorem. Okay, the oscillations will be Gaussian. Of course, there are other literatures which show that if you are not in the central limit theorem assumptions, you may end up with processes that are not Gaussian. Okay, so just to be careful. Most of the cases, things will end up being Gaussian, but this is not always the case. As already we know, in probability, if you sum independent random variables, okay, that really depends on their moments. Anyway, if you are in the case of Gaussian approximation, actually you can show Gaussian approximation in the so-called initialization. So when you just pick random and independent parameters, but also more recently we were able to show that this Gaussianity is also preserved in the so-called posterior or after training regime. Essentially, what we're able to show is that if you insert the data and you want to find the best network after you've seen the data, and this is made precise by using a posterior distribution in the Bayes sense, or using a training procedure in the more realistic situation, because this is actually what people do in practice. Well, even after you've introduced the data, if the data, okay, is not too much, this is a point I should specify, because these are results that work for a fixed family of the size of the data set. Well, anyway, you will be closer to a Gaussian. Okay, so these are just the three kind of bounds we can explicitly say, more or less explicitly give. And of course, these are rates of convergence between a Gaussian process, a Gaussian random variable, which is our simple, if you want, approximation of the neural network, and the actual neural network. And these bounds are given in terms of a very natural quantity, I want to emphasize, that is the so-called Wasserstein distance, Wasserstein or Kantorovich distance. What is the Wasserstein distance? I think I have just one slide here, if you've never seen it. So it's a natural way to compare two probability distributions. Assume that you have two distributions of probability or of mass, and you want to find the simplest way to compare them. In which sense? Well, you may think of these probability distributions as the law of two random variables. And so if you realize the two random variables, each one with law mu and the other one with law nu, well, you can compute actually the LP distance between them. Okay, you just do the expectation of you do the Euclidean norm. For example, you take the Euclidean norm to the power p of the difference, and then 1 over p. Okay, this will be the usual LP distance between random variables. So the Wasserstein distance, if you want, is the most efficient way, so the smallest LP distance between the two random variables among all the possible random variables that have the prescribed laws. Okay, now the motivation, maybe this is not the first way you see many textbooks to define the Wasserstein distance, because typically this is done in terms of couplings and other constructions. And actually, historically, it was introduced by Monge and then Kantorovich more in the sense of measure theory than probability. But in this sense, if you want, it appears quite naturally as a way to compare two laws of random variables. So instead of thinking of two random variables that already are defined somewhere, you just look at the best way to define jointly x and y with the prescribed laws, and then you compute the usual LP distance between the random variables. Okay, so you minimize overall the possible joint definitions of x and y. Now, this is quite a natural distance. Sometimes with a small abuse, I'll write just the distance between the random variables instead of their close. But remember, this is just a measure of a distance between the probability distributions, not the actual random variables. And it's quite simple to show that convergence in terms of this distance actually amounts to convergence in low or weak convergence of their distributions and convergence of the moments. Okay, so the exponent p is not really there to be fancy, but if you have convergence in Wasserstein p, it means that you have also convergence of LP moments. Okay, sometimes you're interested also in convergence of the moments, so this is quite reasonable to ask. Okay, so of course, this is a very classical tool by now, and in the recent 20, 30 years, there's been really an explosion of applications of Wasserstein distance of different orders in different areas like geometry and the PDEs, but also statistics and probability is quite a reasonable tool to use. So in our case, we want to focus on as I told you, neural networks. Actually, our result, to be fair, applies to so-called fully connected architectures, the one I showed you with a picture before, but there are many other architectures. I'm not completely sure at the moment, because I have a slightly more general result, but I'm sure some architectures are not covered. I'm not sure, for example, about convolutional architectures, so it would be very interesting to tell more about this. But for the moment, let's stick with the fully connected architectures. The one I showed you before, just to fix a bit more the notation, I told you there are these layers. So, and if we include the input and output layer, you end up with L+1 layers. And the sizes of the layers, which are just the dimension of the intermediate vector spaces, you have the input layer, which is n0, and then n1, n2, up to nl-1. These are the hidden layers. And then you have the output layer. Now, in our limit, the input and output layer dimensions, sizes, will be kept fixed. And the wide limit means essentially that n1 and n2 and n up to l-1 will go to infinity. Okay. Now, of course, these are just bounds, so you don't need them to really go to infinity. You can just an inequality that will I'll show you in a minute, that is quite effective when the network becomes very wide. Now, to be more specific about these weights and biases, the so-called parameters of your network. Now, the weights, as I told you, are the matrices that appear in this linear transformation, and the biases are just because you consider affine transformations. But actually, this is just I mean, from a mathematical point of view, they're not very relevant, because you could always promote, if you want, these weights and biases in a larger weight matrix. Okay. And finally, what's important in our result is the activation function. Now, the activation function, as I told you, is a very simple non-linearity, which acts component-wise. And usually, for example, we can denote it with sigma. So it's a function from R to R. For example, the ReLU function, so-called rectified linear unit activation function, is simply the positive part. You see, it's a very simple function. And usually, they are smooth, but not too smooth. But in our case, we can cover Lipschitz activation functions. So, for example, this ReLU activation is a good activation function for our theorem. If you take, for example, the Heaviside function, which was the one proposed, I think, by Rosenblatt in the 50s, it's not Lipschitz, it's not continuous, so we cannot actually cover this example in our case. Anyway, so, and then what is the mathematical definition of this fully connected neural network? So you start, as I told you, with a linear affine function, which takes the input and transforms it in the first hidden layer. And then you iterate by taking the component-wise application of the nonlinearity, and then you apply the linearity. Okay, you can also split this recursion into two parts. So you first have the so-called pre-activation, then you apply the activation sigma, and then you apply again with another affine function, you get the pre-activation in the next layer. So just to show you again the picture, so you start with this input, then you apply the affine function, then the nonlinearity, and again the affine function, and so on. Remember, in the output layer, we don't have the pre-activation, okay? So the output layer is simply linear affine function of what you had before, okay? Now, with this notation, I can finally tell you about our result. I think I will go quick and not give ideas about the proof, but these are very simple. And I told you, the interesting part is somehow is that you can get a quantitative bound, but also a very simple proof. So you get somehow it's a good spot between complexity and having a result which is also applicable and interesting from maybe a practical perspective. So, as I told you, this result is obtained by me, but also with Basteri, a former student of mine. So we consider weights and biases in the previous notation that are independent and Gaussian. Okay, now here I say Gaussian, and it's quite important in the proof, but you can extend this kind of argument to non-Gaussian weights. Now, if the weights are Gaussian, it's not completely obvious that the resulting neural network will be Gaussian. okay, because there are no linearities in between. But anyway, let's start with the simplest possible weights. So we start with the weights W that are matrices, and these are centered Gaussians, and the covariance, or better, the variance, because these are independent, so the covariances for different entries will be 0, but the variances are rescaled like 1 over n of L. What does it mean? It means that as soon as the network becomes very wide, all these weights will become very small. This is not something that we come up with. It's something that was already known in the literature. Also, it has practical implications, because it tells you that if you have a network which is very wide, you have many parameters, but you don't want to start with very large parameters of order 1. The parameters must be tuned to be a bit smaller. Okay, taking into account the width. And precisely in this scaling, this does not apply to the bias. The bias must be just variance 1. Now, if you argue in this case, you can fix any set of inputs and look at what happens to the output of the neural network. So as I told you, the neural network will combine the weights and the biases in nonlinear ways, because you have also the activation functions, and also you are iterating, so you're multiplying the weights. So what you can prove in any way is that you are close in the Wasserstein distance to a suitable Gaussian random variable. Okay, the Gaussian random variable, let's denote it the GL. It will be a variable which takes values in the same dimension as here, because we take the input as size k, each output will be NL, so after all you can collect everything into a big matrix here, NL times k. The Gaussian random variable will have the same dimensionality of the output. You can compare the two, and you can actually show that up to some constant c, which does not depend on many things, but let me be clear on what is the dependence. The dependence is in the input set and the exponent and the number of layers, but not on the width. So the width is really explicit and is like the square root of the output layer, and times the sum of the inverse of the square root of the hidden layers, so the hidden layer sizes. Now you see this kind of inequality. Also see, I'm keeping here implicit, but in principle you can work out some bounds of this C. Now the interesting part is that it applies for, say, a large variety of architecture, say activation function and so on, but also shows that when the hidden layer sizes goes to infinity, so this NL grow, this distance will go to 0. So we're getting closer and closer to a Gaussian random variable. I want to tell you anyway what is this Gaussian random variable. The point is that this Gaussian random variable, which is the so-called wide limit Gaussian process for the neural network, also known as neural network Gaussian process, is more or less explicit. So there are formulas, there are recursive formulas. I'm not putting them here, but if you look at the literature, also the preprint, we cite the well-known formulas. But also there are even numerical libraries, for example, written in Python, that can compute numerically these covariances of these Gaussian random variables. So somehow we are able to quantify the distance. Another interesting part, maybe it's not so obvious from here, is that even if the network is very wide, what happens is that the rows, the vectors of the output, will have independent rows. Okay. I mean, the columns may be dependent. So if you take many inputs, there may be correlations between different inputs, but the rows will be independent. And also, okay, let me skip about this deep limit, because we cannot really say very much about the deep limit with this kind of result. There are other literature which explores a bit more the deep limit, maybe more in a qualitative way. Now, about the proof, maybe just one comment on the proof. The proof is really, say, a careful combination of what we already had in mind. Essentially, this goes back to Neil, the idea. The idea is that you have each layer is tuned somehow to be a central limit in the central limit theorem regime. So you have these weights which are small when the network becomes very wide. And also, there's this other idea, if you go back to Neil, essentially is almost there. The point is that the neurons, even if you are combining them, I mean, the others combine all the neurons if you go from one layer to the other. The point is that when you are in the wide limit, these neurons becomes almost independent. Okay, so the crucial point is how to quantify this almost independence. If you go really straightforwardly, you end up in a bit of a messy of an argument. But the point is that if you are careful with the induction, you can really show that this almost independence is captured by the quantitative error using the Wasserstein distance. Okay, so this is really a case where the idea is there, it's very clear. But if you look around at the literature, there are many ways you can make it precise. And I hope, I mean, what I like about this result is that if you look at the proof, it's very simple. It's one page of computations, follows very straightforwardly from the properties of the Wasserstein distance. So somehow here is a win for the Wasserstein distance compared maybe to other possible approaches. Okay. Now, of course, you can also try to simulate and see what happens in reality. Can we really validate our result? Now, this is instead a bit of a problem for the Wasserstein distance. The point is you need to compare the two distributions, right? Now, for the Gaussian random variable, you know, more or less, you can compute the distribution because you know the mean and covariances, because there are these formulas, these numerical libraries. Now, the real issue is to get the distribution of the neural network. Now, how can you do it? Well, you can just sample randomly these neural networks. So you will have a sort of point cloud of the outputs of the neural network, and you want to compare it with the Gaussian. How do we compare it? Well, essentially, we also sample the Gaussian, and we just compute the distance not between the neural net, the theoretical distributions, but between the so-called empirical measures. So we just compare the two point clouds, how close they are. And essentially, it is known that if the number of points is very large, you are not doing a large error. Okay, you can really compare the two empirical distributions and get an estimation for the theoretical distance between between the two theoretical distributions. Unfortunately, this error becomes large if the dimension grows. Okay, when you are doing this thing of point clouds in high dimensions, as far as I know, these errors, I mean, there are precise estimates and they become non-negligible in the sense that you have curves of dimensionality. So essentially, Wasserstein distance has a lot of good properties, but it's affected by the curves of dimensionality. In our case, this means that if you take many points in the input set and a very high dimensional output vector, it will become very difficult to estimate. And you're going to see now in the simulations. Essentially, these are just, as I told you, the outcomes of our simulations. The blue line is the empirical error, the distance between the Gaussian point cloud and the neural network point cloud. And you see that if the number of neurons grows, it's okay. And here we are just taking a six-dimensional input and one-dimensional output and one input point. So this is really the best we can do. This is really a one-dimensional problem. And we go back to machine precision, if you want, well beyond our theoretical error. But if you let, for example, the number of input grows, you're already here in the two-dimensional thing. You see now this becomes flat, not because we are wrong in our result, but the point is we are hitting this error with the numerical approximation of the Wasserstein distance. Actually, if you go even beyond, now maybe here I'm not listing, if you go even beyond, now we don't see it, I just removed the bad simulations. At some point you really cross the theoretical error because we are doing too much. I mean, the precision is not too much in our simulation. So if you want, it's a good numerical problem to come out with good, smart ways to, if you want to capture this kind of result, validate for really large networks this kind of result. Of course, we know it's true because it's a proof, but it's already something interesting. And it's already a problem per se. I mean, to estimate the Wasserstein distance between high-dimensional distributions, high-dimensional point clouds. So anyway, if we stick with our simulations, we see we agree very much with our theoretical error. And actually, the slopes, you see, I'm writing down here the slopes. The slopes will be corresponding to so we would expect a -1/2 because we have a rate which is sum over the inverse of the square roots. This is in log coordinates. So you would expect a slope to be -1/2. The point that numerically we found much better slopes. You see minus 0.8, even if you change p's, you do one distance, you get minus 0.8 and so on. These are just numerically validated. So the point is maybe our result is not so good as it seems. Now here, don't worry, it's just because we never changed the scale of the theoretical error. I mean, even in this case, the slope is minus 0.5, so which agrees with our result. So, but the question was whether you can do something better. And actually, in a more recent work, Stefano Favaro from Torino and Giovanni Peccati, Marinucci, and Boris Anin, maybe I forgot someone else. Anyway, they showed that you can actually improve this kind of rates, at least in the one-dimensional input and output. They showed that actually you can prove a better rate. Essentially, the rate we proved was not sharp, because the best rate is 1 over square root of n. So n I are always the hidden layers. So you may say, okay, this is not so much of an improvement, but actually you see it from simulations already. So it's something that was quite open. Unfortunately, what I have is a condition, which I don't know. I mean, we know it is generic, but it's a condition. So they impose that actually this Gaussian process is non-degenerate. So what does it mean? It means that you have a positive, strictly positive variances. Actually, not only at the output layer, but also there are intermediate Gaussian approximations for the hidden layers, and all the approximations must be so-called non-degenerate. Okay, but if you require this, automatically the rate improves. Actually, we recently were able to improve a bit more. For example, here they say you need a single input x and one-dimensional output. Actually, this is a more general phenomenon. So as long as the Gaussian process is non-degenerate, so it means that it has a density, you can really improve the rates, and the actual rates go like 1 over n and not like 1 over square root of n. So in practice, it means that this Gaussian approximation is very, very good, is much closer than what you would expect. Actually, what I don't know, because it is known that these rates cannot be improved, so cannot be better than 1 over n. But if you are interested, this is quite a question that I never considered too much, is whether if you remove the assumption that the weights are Gaussian. So if you take weights that are, for example, discrete, Bernoulli or some other distribution that you may like, maybe the rates cannot be that good. Okay, this is something that, as far as I know, is still a bit open, but maybe just an exercise. So anyway, the point is you can really improve these rates. And maybe I'll skip a bit about the proof, because I want to move to the posterior bounds. So the point is, so far we're just describing what happens if you take a random neural network, a generic neural network, which is very, very wide. Now the point is, can we use this result? What does it say about what we actually want to do with these neural networks, right? So if you just stick with the simplest application of neural networks, which is, if you want, the framework of supervised learning, which you can do also without neural networks, but of course it's nowadays more, so it's fancier to do it. So you have a training set, so you have a set of inputs xi and outputs, corresponding output yi, over a finite set of points, for example, images of cats and dogs, or dogs, and yi is a vector which, for example, is +1, is one dimension, is +1 if it is a dog, and -1 if it is a cat, right? So you want to do a classification. So you want to learn a function given this set of example. Let's call it h, this function, which after all will be our neural network, which takes an input x and gives you an output h of x theta, sorry. Theta is a set of parameters. I want to select theta so that, of course, h of xi, at least in your training set, is close to what you know it is correct, because of course, you expect the training set to have the correct data, right? But also we would like to generalize well to previously unseen data, right? Otherwise, you are just interpolating your training data set. Now, of course, there are many ways to approach to make more precise this problem. If you study a bit of statistics, you know there are at least two approaches. One is a variational or frequentist approach. So you fix an error, a misclassification error, if you want, or if you're doing regression, you just take a mean square error, for example, so which computes how large is your error. Then you may also like to add some regularization function, so which is a sort of a penalization for parameters that you don't want to have, right? And then what you look for a minimum, so generalized least square optimization, for example. So more generally, you minimize the so-called empirical risk. So you look among all the parameters, those who minimize the sum of the loss, okay, plus the regularization, right? Of course, this is a traditional variational approach. You can also think in Bayesian terms, if you like. So you may think of fixing a likelihood function, which is, if you want, the probability of observing your training set given the parameter theta is known, okay? So this tells you essentially how probable is to find your training set if you have already the knowledge of theta, what is the correct theta, but this must be specified for all thetas, all the parameters. Then you may specify also a prior distribution upon your theta, because you may have reasons to specify that your theta, you want to have it in some regions and not others. And then if you use Bayes' rule, you can compute the posterior. The posterior is simply proportional to the likelihood times the prior. And then if you just want a pointwise estimate, you look for the mode, so the theta which maximizes the posterior. So this so-called maximum posteriori estimate. Of course, these two approaches are very much related. Now, this is a slide I always keep, but people, I either say that it's trivial or not. It's very illuminating. So essentially, there's a simple correspondence between these concepts, right? Because if you're given a likelihood, you can take the log and change the sign. Instead, if instead of maximizing the likelihood, you are minimizing something, and actually you end up with something which corresponds to the empirical loss, the sum of these error terms. And also the prior, if you take minus a log, you end up with an object which looks like a regularization function. And also then the posterior, given that you have this correspondence, this logarithmic correspondence, really corresponds to the empirical risk. So essentially the Bayesian approach, at least if you want to find the maximum a posteriori, can be set in correspondence with the variational approach. So in particular, for example, if you start with a likelihood which is corresponding to a mean square error, what does it mean? It means that you are assuming that given theta, if you know theta, the residuals must be Gaussian and independent, because the density, the probability of observing these residuals is exponential of minus their squared. Okay, so given this correspondence, now in practice, people use mostly, at least for neural networks, people stick with a variational approach. So if you look at a general recipe to find a good parameter, you will have something for the variational point of view. But for our kind of result, the Bayesian is more natural. Why? Well, because, as I told you now, the deep neural networks are already parameterized by these weights and biases. And also Gaussian weights, so the choice of random Gaussian weights gives you a prior distribution over these networks, right? On the other side, also Gaussian processes somehow can be thought as a trivially parameterized family, okay? Somehow the parameters are already the value of the function, okay? Okay, this is quite trivial if you want, or can be made precise in other ways. So somehow our inequality about initialization tells you that the prior distributions are very close in the wide limit. So you can think about maybe this prior inequality can give me something about the posteriors. And of course you can prove it. You can prove it if you have some assumptions. So essentially the point is, if you have a likelihood, which is a function that is Lipschitz, now the choice of Lipschitzianity is due to the fact that we're using the Wasserstein distance. So it's related to the so-called dual formulation of the Wasserstein distance. If you have a bound in other distances, you can also have a different condition on the likelihood. Anyway, for example, the Gaussian likelihood, which corresponds to the sum of squares, is mean square error, sorry, is Lipschitz, okay, because it's exponential minus square function of this z. So it must be Lipschitz. Just be careful on the function evaluated on your training set, okay. Now you can pick any other finite test set and define the overall input set big X here. Now what we can prove is that, of course, if you take a neural network, the posterior distribution will be proportional to the likelihood times the prior, and also if you have a Gaussian process, the posterior will be proportional to the likelihood times the Gaussian prior. Now what we can prove, I'm skipping also a bit of technical details here, is that under mild assumptions, like for example that the expectation of the likelihood is strictly positive because this appears at the denominator, okay? Then if the network becomes wide enough, well, also the Wasserstein distance of order 1 between the posterior will be close. Actually, they will be close like constant times square root of n. And if it is non-degenerate, you can improve up to constant over n. Anyway, the important thing is that you can really show that quantitatively also the posterior will be close to each other, right? So in particular, if you start from the simplest case, which is the mean square error case that gives you this likelihood here, well, actually, you can prove that the posterior, this is well known, essentially the posterior, if you start from a Gaussian process, will be also a Gaussian random variable. And actually, you can compute the mean and covariances of this posterior. So you can show that also the neural network, after you've seen the data, at least if you look at the Bayesian posterior, is close to a Gaussian, okay? So you have this correspondence, somehow they have this continuity of the operation, of the distance with respect to this operation of taking the posterior. Of course, we have specific assumptions, but you say it's a general principle that can be applied also in other models. Now, let me just conclude with what we're working currently on, because people may be satisfied with the posterior if you are a Bayesian statistician, but the point is that in practice, people do not look at the posterior. It is well known that the training procedures, so that you select the optimal theta star, is not really doing the maximum a posteriori, okay? Actually, the best theory so far, at least in connection with the Gaussian approximation, is this so-called neural tangent kernel theory, which tells you what? Well, it tells you that if you start with a nonlinear model, nonlinear in the sense that is nonlinear on the theta, on the parameters, well, you can say linearize it and define an object, which is the so-called neural tangent kernel, which is simply, if you want, a Jacobian matrix in terms of your theta, right? So you take the derivative of your model with respect to theta times the derivative of the model transpose, okay? Now with this kind of object, sorry, there is a gap here. You need to evaluate possibly at different points, like x and x prime, okay? So you have an object which is, if you want, theta zero, think of theta zero as fixed, your initialization. You have a big matrix, a big operator on your input space. Well, what can be proved is that, which is somehow independent or at least orthogonal to this Bayesian idea, is that if you have a very deep network, you can show that almost surely, given again this kind of initialization, as I told you before, you take random Gaussian independent parameters. Well, anyway, in the limit, in the wide limit, you will converge to a deterministic object. And this object typically is denoted with big theta L, because we have a network with depth L, will be again a function of your pairs of inputs, and this is another kernel. So it's a kernel in the sense that it gives you a positive semi-definite kernel, okay? So what does it mean? It means that we have another possible kernel which may be different from the covariance of your neural network Gaussian process. And this kernel is called the neural tangent kernel. What is the role of this kernel? I'm going to show you in a couple of slides. The point is that this kernel captures a bit what happens during the training by gradient descent, and also possibly other optimization algorithms. Okay, typically the theory is performed just studying gradient descent. So, for example, think from a variational perspective. Now, we want to minimize find the theta so that our mean squared error loss is the smallest possible, right? I just multiplied by 1/2 to simplify the numbers here. Now, how can you find the best theta? Well, you start from some initialization, possibly random, and then you perform gradient descent. So you just update theta t according to a small step, depending on so-called learning rate eta, which is, if you want, a small parameter, times the gradient, minus the gradient with respect to theta of your E, of your energy, right? So you're performing small steps along the best directions that locally minimizes your energy, right? Now, of course, if you go to continuous version, you end up with the gradient flow equations. Now, but whether you choose gradient flow or gradient descent, the point is that if you now look at a point xi, at the evolution of your h, well, you end up, now this is a computation one should do at the blackboard at least once. Anyway, you end up, with an equation which looks like a closed equation. Essentially, if you apply the chain rule, so you have the gradient of h with respect to theta, and then the update of theta, well, you end up with an equation which looks like a closed equation in terms of an object, which is our neural tangent kernel. Well, not the big theta, but you have a neural tangent kernel that depends on the theta t where you are at during the algorithm steps, right? Now, of course, this is not a closed system of equations. Even if you collect all these equations for every xi in your training set, you're not able to close them, because even if h appears on the right-hand side, you have this NTK that you need to compute. Now, the insight by, if you want, is already in Jacot, but also Montanari and Lee, and so a lot of literature recently, is that really when the network becomes wide, and if you rescale, if you do a suitable scaling limit, here I'm cheating a bit, the point is that this neural tangent kernel will not evolve. Okay, so you will have the network will evolve, but this kernel, big theta, will stay the same during all the training. So at least for every finite window of the training. So at this point, you can really substitute in this equation, not this NTK, which depends on theta t, but the original big theta L. Okay. And so what does it mean? It means that if at initialization you have a Gaussian process, during the training you evolve with this set of equations, which simplify a lot, which are linear equation driven by this NTK. So you can say that also during the training you should be close to a Gaussian process. Okay. Now, this kind of results, this kind of analysis is performed with different degrees of detail along the literature, but so far as we know, nobody gave full rates of convergence in terms of Wasserstein distances. So recently we're still working on, but we're able at least to cover the shallow case with Agazzi and Mosig. We're working in the shallow case, but we also have results in the deep case. So we're able to show that actually not only at initialization, so not only the exact posterior, but also during this kind of training, you can show that the Wasserstein distance between the actual neural network, which is trained over this training set using gradient descent, and the solution to this differential, so it's just a finite dimensional linear equation at this point, initialized in the Gaussian process G at time 0, the one that we use in the past, in the first result. Well, the distance stays small, and we can actually bound it. Okay, maybe the bound is not very nice, at least to see it from here, but the interesting part is that, of course, when the network becomes wide, it's okay, it goes to 0. But also there's an interesting catch here. You see, we have something that grows with t, so which means that actually this approximation may not work for very large times. Essentially what we see here, and in our proof is there, we're not able to remove it, is that there may be some bad event where these things, this approximation fails, and we are not really able to say to bound what happens to the network. So we suspect that this kind of result, maybe the exponents are not very sharp, but the shape of this bound may be sharp. So there may be something that diverges as t grows. Okay, but still, this is a bound which I think is a first of its kind in this kind of literature. Okay, so in conclusion, as I told you, we are able to give approximation bounds, which are more or less explicit. You can work out explicit constants and other things, both at initialization for the posterior and during the training, at least in this NTK approximation, in this NTK regime. So the other questions, there are many questions, for example, different training regimes, because not only NTK is a possible description, but there are also scaling limits, different scaling limits for the training, and so far we're not able to capture this kind of trainings, and also more general architectures. As I told you, yes, neural networks are very old as an idea, but new architectures with specific structures are very relevant for the applications. For example, recurrent neural networks or transformers are, I mean, state of the art in many fields. While the multi-layer perceptron, this kind of, it's a sort of a toy model of what a neural network should be. Okay, and then if you're more interested in the theory, yes, as I told you, these kind of results are about a fixed input, a fixed training set. So a natural question is whether these results can be extended to infinite input and to get sharp functional bounds. So far there are functional bounds, but as far as I know, sharpness of this kind of bounds is not known. So the role of this 1 over square root of n or 1 over n is not completely understood when you take infinitely many inputs. Okay, so here is some literature, but it's not maybe the most updated literature. I just want to highlight this paper by Favaro, Hanin, Marinucci, Nurdan, and Peccati. Yes, this is the complete list of authors. If you look at these references, you can find more recent mathematical works on this side of the literature. So thanks a lot, and if you have questions, I'm here. I hope.
But we have many.
Okay.
Just to warm up, let me start with the trivial one. So in your last theorem, the one with Agazzi and Eloy,
yes.
So how likely is that the minimum eigenvalue of θ2 is positive?
Yeah. So about that, there is a result about. So this is actually a generic condition. There is a paper, not by us, but a group, I think from Portugal. They showed that if the nonlinearity is non-polynomial, if the nonlinearity sigma are not polynomials, for points in generic positions, the NTK and also the NNGP will be strictly positive. Of course, then you may ask, how far am I from being
from
zero?
Right? Yes. Yes.
So, and then there are other results that for example, I think by maybe Guido Montufar, I think they showed, or also Montanari, they studied, for example, if the points are in a sphere, you can really give lower bounds for certain.
This theorem are most sure theorem. It is a most sure.
Right. Yeah. But here we think about the limit one, right? The NTK. Yes. These are almost sure in the sense of the points, right? They take infinitely many points. Yeah. Somehow, again, these are in the sense that you should think of this non-degeneracy condition as being really generic. I mean, as far as I know, the most satisfactory result is this about the non-polynomial activation functions, which tells you, yes, it's not a big deal asking that these are strictly positive.
Oh,
I mean,
thank you.
If it is non-positive, there must be something strange in your the choice of points or the structure of the network, right?
Thank you, Dario. So,
yeah.
There is a question by Gianluca.
Yeah. So, thank you very much for the nice presentation, Dario. I have a little question. So, in the first part of the talk, you presented your prior bounds, and okay, so you gave this rate for the Wasserstein distance 1 over square root of n, where n is the minimum of the number of neurons in the interlay. So we know that this can be improved to 1 over n. Okay.
Yes.
Okay. In a sense, so the Wasserstein distance. So if you consider the Wasserstein 1 distance, so in a sense we can consider this distance as a smooth distance because due to the Kantorovich duality, you have the supremum over Lipschitz test functions. So,
yeah.
So you know, there are similar results with the same rate 1 over n, for instance, for non-smooth distance like the Wasserstein, and not like the total variation. So I know that when the dimension of the output is equal to 1, so there is a result in that paper by Ani and Peccati where they prove that the optimal bound is 1 over n. But I think the general...
Yeah, I think there is a paper now. I haven't checked the details. There's a more recent work by Peccati and Celli, I think, where they do also relative entropy bounds, and maybe they also have something about the total variation. Yes. So one question, yes, you're right. You say if I change the distance, how good is the bound? Should be checked. As far as I know, there is this paper where they also do something about relative entropy, which is not really a distance, but you know, can play a similar role. Also, is related.
So so you think that if we use these relative entropy bounds, maybe we can reach even bound like 1 over n for the total variation.
Yeah, I mean, I'm not completely sure, but I guess
yes.
Something could be done. On the other side, it would be better to maybe to relax, so to find distances, or I mean, we have this barrier for the Wasserstein distance, right? You say 1 over n cannot be better, but for example, you maybe more interesting to say if I change the distance, maybe I can get even better bounds, right? For example, if I do duality in terms of smoother functions, and I do a smoothed Wasserstein distance, you take a convolution with a small. So maybe more interesting to get more flexibility in terms of the choice of the distance, because this idea of Wasserstein distance is useful in this case because it gives you a simple argument and it's strong enough. But maybe for different applications, you would like to have a different notion of distances. So yeah, there are many things to explore for sure in this case.
Thank you.
Just one more question. Sorry, just because you were so clear. So this is mostly curiosity, but I don't know whether it is trivial to ask that question, but I ask. So consider, for instance, a model, a linear, a fully feed-forward linear neural network. But this time, what you think? What is your guess? If instead taking random Gaussian matrices, I take matrices with constrained support, that is, they cannot assume all the values in their range. What do you think? This limit theorem, it is something like a constant application of ReLU in one direction. But do you think that your bound can still apply in this case?
You mean if the functions, if these are smooth, so you have weights that are uniform on an interval, for example.
For example.
Yes, it should apply. At least the one with 1 over square root of n, they should work.
This should work.
Yes, I think it should work. An interesting part. The point is the one with the bounds with 1 over n. They seem to be trickier, because at some point we use even if you do in the one-dimensional case, they use a bit of Malevin calculus. So perhaps any distribution may be. I mean, if you have a Gaussian distribution, you have specific tools. well, if you have any distribution, maybe not even without a density, yeah, you don't have it. So there are some tools that are available for the Gaussian distributions or Gaussian-like distributions. But if you have something which is far from Gaussian, it may not work. Yeah.
Thank you, Dario.
Yeah.
And so there is a question by Giovanni Francina.
Okay.
Hi. Thanks again for your talk, once again. I have, again, a question about the more recent result of yours about the NTK regime. I remember there were some papers that got many citations in the community of computer science, in which the people, more or less, if I remember correctly, maybe Nicola will correct me, they were proving that with overwhelming probability, you had some upper bound to the time you need to get your empirical risk smaller than some threshold. So the time you need for your network to be close enough to the target. Exactly, your T.
Yes.
And of course, in the proofs, I mean, this lower bound for the lowest eigenvalue of the deterministic NTK was playing a role. Is there a connection with the result of yours?
Yeah. Yes, exactly. If you want, this point, this last result I'm telling you is about, if you want, reading again this kind of result with a quantitative eye. Somehow you want to quantify everything. So first of all, you need to quantify how close is the convergence to the NTK, from the empirical NTK to the theoretical one. But then also all this training procedure. So, and in all these kind of results, you have, yes, with very high probability, this good event, you are in this good event, the NTK will be positive, also the empirical NTK will be positive, and so on. But then we have the bad event. So somehow the bad event, because the Wasserstein distance takes all the distribution and wants to fit it with all the other distribution. And the cost you pay is the distance to some power p. So you may play a bit, you may cheat a bit and say, okay, if this I can just match most of the distributions, then maybe I pay a fixed price for what is left, and somehow you are quantifying convergence in low and without any consideration for the moments, right? So somehow all this, what we're trying to do is to quantify the bad event. And we suspect, but we are just on the line of upper bounds, but we suspect that there must be some exceptional event where things go really bad and the network explodes, so they become very far, the linear approximation, the Gaussian approximation and the actual neural network. Of course, you may say, well, in practice, this may be an exceptional event, I don't care about it, but of course, it depends really, again, on the kind of result you want to prove. If you want to do the result in Wasserstein distance, this pop up. If you just want to say, I exclude an event which is small in probability, and then I really don't care what happens there, yeah, maybe this is already known, right? Right. I hope this clarifies. Thanks.
Let us thank once more Dario for his very, very nice seminar.
Thank you.
We are in next autumn.
Next autumn, we have other second part of the seminar.
No, I promise. Thanks again. Thanks again. So let's keep in touch. We'll see you in the future.